So we're going to talk about the aldol reaction and diastereoselectivity. So diastereoselectivity at first is just about getting essentially the two groups that you're making. You're only making one diastereomer, so things are either going to be cis or trans to each other. It's not yet enantioselective, right? Diastereoselective means you're making one of the possible diastereomers. That still means you're making enantiomers of those diastereomers. All right, so let's take a look. What do I mean by all this? Let's just show an example. So you got a ketone. It's going to get deprotonated, so you're going to make an enolate. Let's just start there. We're not going to worry about what X is. We can add something to X. Essentially what X can do, right? Because at the end of the day, something's going to end up going, well, this X can influence how this attacks, right? This X can influence, essentially, right, the resonance form here, which is more of an enolate, right? They're both enolates. I take that back. They're both enolates. And there's X. This X can influence, right, how this pi bond attacks, right? Because this pi bond, of course, is flat. But what is on here can influence how this attacks, whether it attacks from the top or the bottom, those kind of things. So we end up making this enolate, and this is a Z enolate, right? And that's the one we always form, a Z enolate. That's important too. Why we do that usually is because X is big enough where X doesn't want to be near R, so O minus is actually the best of the worlds, right? So R is up here, we got to choose which one's worse, the O or the X being by it. Usually X is bigger and it makes it worse. So that's why it's technically a Z enolate. Even though, right, this X is usually a nitrogen but with a bunch of stuff on it. So right, even though it's Z, because oxygen has priority, so called a Z enolate. That matters because that means we're only getting, right, one version of this is Z enolate. So when we react this with an aldehyde, right, these things are going to come together in a certain way. Now along the way, I haven't shown it here, lithium, to balance our charge, let's say you have to have some sort of metal to help balance our charge. So lithium is actually going to act as a surface to bring these two things together. Right? Because you can imagine here, we numbered our things. We have 1, 2, 3, 4, 5, 6. We're going to get into a ring, a chair conformation here. And the lithium is going to be the thing that binds the enolate and the aldehyde together. Right? So the lithium is going to bring things together in a certain way. And this being a Z enolate matters. So let's see what that looks like. So let's draw the lithium here. So lithium, we'll say the lithium is actually fully bonded to the enolate part. We'll put X down here. H is going to be pseudo-equatorial. R prime is there. We also have the aldehyde coming. And we'd rather have the R2 be kind of equatorial and have the H kind of hanging out down here. Right? So you see, right, if you look at this, right, we call this a syn aldol usually, because look at the R groups, right? They're both. If you think about this as a 6-membered ring, right, this is the bond that we're forming right here. They're both kind of pointing up on the ring, right? This is an axial up, this is more of an equatorial up, but they're both kind of pointing up, right? So that's what happens. That's how the electrons move. So this is a transition state. So we get the R and the R1 and R2 are essentially syn to each other. That's why they call it a syn aldol. So the electrons attack. These would come down. Attacks there. These electrons go then to the lithium. What does that look like? We switch things around a little bit. Still have the lithium there. Oxygen. This is now a ketone, or, yep. formed a new bond there. R2 in the equatorial position, R1 axial, H equatorial. This other H is axial down, back there. So as you unfold this, right, the syn part again, the R's, R1 and R2 are syn to each other. Right. Or you could say the OH and the R1 are also syn, but I like to think of it as the R groups that are syn to each other. It's just easier for me to see. So, there you go. So that breaks down, and that'll look like, right, if we look at the actual picture here, what does it look like? So the final product will look, there's our X, OH, R1. So the R1 and the OH are on the same side. That's kind of the syn part. You can see it. I like to look at it the other way too, is the R2 and R1 on the same side. But that makes one set of diastereomers, right? So that becomes diastereoselective because, right, you're only reacting the Z enolate, right? It's only reacting in a certain way, right? You always have the Z enolate. So the oxygen and the R here are always on the same side. Right? They're always on the same side. Now, another layer you can add to this is dealing with this X, right? Dealing with that X. Or we talked about before, where if this X was something that could affect how this pi bond attacks, this pi bond, right, this enolate might only attack one certain face of the aldehyde. And if you do that, if you pick one face, now you're making one enantiomer, not just a diastereomer, right? Diastereomers can be like cis or trans, right? That's what we call a syn aldol, right? So we're getting only the syn product. That's one diastereomer. But now we're going to take it up another level and say, well, if we have a chiral center here, an X, that's going to influence how this enolate attacks that aldehyde, and only pick one face of the aldehyde, and that'll give us enantiomers. Okay, so right now, this could attack that side or the other side. There's no preference. We're always going to get the similar relationship between the OH, in this case, and the R1. They're always going to be syn. But we could also get, right, what could we also get? We could also get the other enantiomer of this. Right, what would the other enantiomer of this look like? The other enantiomer would look like this. We would just, right, we put R here, put H there, H there, OH in R2. Right, so we get both of these. These two things are enantiomers to each other, but we only get this style of diastereomer, right, where the OH and the R1 are always cis to each other. So this is diastereoselective. But the next level we're going to take it, what if we could only get one of these? What if we only would get one of these? Now that's possible, right, because these are enantiomers. So how do we make this reaction enantioselective? We make it enantioselective by making the X group be something like this. Where that's what's attached. All right, we make the X group have an asymmetric center itself. This asymmetric center is going to influence the formation of these two asymmetric centers. And because of that, we're only going to get one of these enantiomers.
Isn't it the right one?
I don't know off the top of my head. I should go through it, so we'll see which one. Put those over there. Put that guy there for safekeeping. So essentially, we redraw these pictures again. Right? We redraw this one again. I'm going to draw it a little different this time. Why not? Because let's make it more complicated than it has to be. Not really, but we'll do it. So there's our aldehyde. Right? It's going to be coordinating to the lithium, right? It's not fully bonded. Our enolate, which is, of course is always going to be what? Z. There's our 1. There's an H. Right, and now this is where this beast comes in. Right? So think about it this way. This enolate is attacking that aldehyde, but it has this big honking thing hanging off it. We don't want this isopropyl being facing towards that aldehyde, right? We want it pointed away. So as I have it drawn right now, it's pointed away, right? You see that? Right, it's pointed away. I could draw it the other way, right, where this would become, right, if I attack this, so I'm attacking this aldehyde from this side. I could also attack it from the back side, but then this would be sticking into that aldehyde, so it won't work. And this will get me 1 enantiomer, because I'm essentially, what am I doing? I'm picking one side of the aldehyde, right? This is flat. I'm picking this side, the front attack versus the back attack, based on this stereocenter. Right, so the mechanism essentially stays the same. Electrons go down, attack there, electrons go there. It actually gets us to, right, it gets us to this intermediate, which then with H plus will get us to this 1 enantiomer is the one we form in this case. That's the one we form. So we don't form the other one. We will not form this. So that's what this chiral center, this chiral auxiliary, will do for you. It takes a reaction that's always syn, diastereoselective, but it's still making 2 enantiomers. Adding this stereocenter influences the formation of this enantiomer only, because it took this aldehyde and made, right, the face from the front easier to attack than the face from the back. So the big take-home message here is that one stereocenter can influence the formation of another one, so and make it selective.
So if that stereocenter was hatched, it probably could be.
So if this stereocenter was hatched, you'd get this one would be your major product, right? Be just the opposite. Absolutely. All right, looking at number 4 from 2014 quiz 2. First thing we see, strong base. I've already pre-numbered our carbons for us. The most acidic CH, of course, is not the aldehyde CH. That just doesn't make any sense. It's actually the CH on carbon 6, because that's getting pulled by 2 carbonyls. So let's use that to make our enolate. I'm just going to put the negative charge on carbon 6. Now, you were actually given the product here, so I should draw that in before I get too far ahead of myself here. So there's a negative charge there. 1, 2, 3, 4. I even numbered the oxygen, why not? 5, 6, 7, 8, and 9. Our product that we're going to, let me draw that up here, that is this. Numbering our carbons, let's say, well, I hope this is still 9, that's 8, 7, 6, 5, 3, 4, 2, 1. All right? That's one of the first things you got to do. Good numbering system helps. Got to have that numbering system down. So what bond do we need to make here? We know we need to make a bond between which 2 carbons? 6 and 1, right? So let's do that. I got 6 is a good nucleophile. 1 could be a good electrophile, right, in the beta position. So let's attack there. We can have, I'll draw it all the way up this time, making a different enolate. Good numbering system. 5, 9, 8, 7, 6. This is supposed to be 1. 1 is bonded to 2, which is bonded to 3, which is bonded to O minus in this case. 4, 3, 2. There's a new pi bond between 2 and 3. That balanced my charge. I feel like I did. What other bond do we need to make?
3 to 6.
3 to 6. Okay, good. A little bit of an issue there with that, though. A little bit of an issue with that, though, right? Carbon 3, right now, is that an electrophile or nucleophile? It's not really either, right? I mean, oxygen can be nucleophilic, and carbon 2 can be nucleophilic. So that doesn't work. And carbon 6, is carbon 6 right now a nucleophile or electrophile? It's also kind of neither. So this ain't going to work, right? We need to do something different here. So what can we do? We can form a different enolate, right? So you could, there's a couple ways you could do this. We could make it kind of ugly and dirty, which is fine. There is still, of course, a CH here at carbon 6. That's also still between two ketones. Is that an acidic CH? Oh yeah. So let's take that, turn that into a nucleophile. And I think at the same time we could turn this 3 back into a electrophile. So if we're going to do it ugly, let's just do it ugly. That's fine. Somewhere somebody's mad at me. That's okay. Did this really happen in one molecule? No, it sure didn't. Angles just don't work. But I'm too lazy to draw another one of these out. Right on. Right? This is not happening in one molecule. Let the world know that. I'm not denying that fact. But I'm not going to draw a whole other molecule. That's just it takes way too long. And the arrows are the bonds, broken bonds form. It's fine. Sorry, old professors from back in the day. So what we have now is what? We've got our aldehyde back. Let's go back to our numbering system. There's a negative charge here. 1, 2, 3, and 4. 5, 6, 7, 8, 9. So that last bond we needed to make was between 3 and 6. Well, now 6 is a good nucleophile. 3 is a good electrophile. Let's do it. Right, all along the way, right, we could have done this, if we wanted to make it a little prettier, right, we could have used water here, right? In that first step, we made water. So we could have done it a little prettier here and used water to transfer all these things around, the proton. Whatever. It's fine. We didn't. So now let's see. One, 2, 3, 4. Oxygen 4 got the electrons. 6, 5, 7, 8, and 9. All right, these guys are bonded here. I'm sorry. All right. Last step is we can just regenerate that catalyst. OH minus could technically be a catalyst in this case. Regenerate that, and that gets us to our product. Right? Good numbering system. What bonds do I need to make? How do I make one carbon an electrophile or a nucleophile? Right? Think about that. I need to make a bond. Somebody's got to be the nucleophile. Somebody's got to be the electrophile. All right, working on number 5 from chapter 2 problem set. That had this ring, or diene. First step, it was going to react with Na plus, OET minus. Right? So either O-ethoxide can be a base or a nucleophile. Now, in this case, it's going to be a base because, right, we got to remember, aromaticity matters. Right, if I take that H off and put a negative charge on this carbon, this ring is now an aromatic ring. All right. So let's number our carbons. 1, 2, 3, 4, 5. takes the electrons, they go there. Right? Let's see, did I actually I gave you guys the actual product for this too, right? I believe.
Yeah.
So let's look at the actual product. Would be there's two products, right?
Correct.
Two possible products here.
Yeah. It doesn't work the same.
Or and.
Oh no, after this one.
Alright, so just so we know where we're going at the very end here. There's a couple arrows here along the line. So we get the base, deprotonate, make our aromatic product, good and stable. Good. Now we're going to react it with a ketone. Right? So we have a nucleophile and electrophile. You can number these carbons. 6, 7, 8. So 1 is going to attack 7 in an addition step. Right? Addition. Balance our charge. 1, 2, 3, 4, 5, 6, 7, 8. Good. Now at this point, what do we got to do? What do we want to do next? Well, what can we do? We have a tetrahedral intermediate. Do we have any good leaving groups? Nope. Compound's not aromatic anymore. That's not great. This is an aldol reaction. What can you do with aldol reactions? So, when in doubt, right, what do we generate? We regenerated, along the way we made this, right? Yeah. So when in doubt, let's just take that H. So what does that get us? Does that get us anything we care about? Well, right, these aldol reactions, when you attack a ketone, you should be thinking condensation. You should be thinking trying to lose water at some point. Right, because water is a really good leaving group. Well, water or the combination of losing water is good. Because again, look what we've generated. So we've balanced our charge. 1, 2, 3, 4, 5, 6, 7, 8. Now this is fine, right? But again, we're back to the same idea. Carbon 1, is carbon 1 still a CH? Yep, is that going to be an acidic CH? Yep, why? You're making an aromatic product again, right? So let's take that H, let's take another H again.
Can you just make the double bond right away? Or is that more now?
Well, yeah, so that's a good question, right? Do I want it? Well, yeah, I mean, let's talk about it. And that question basically comes down to what are you debating? What two mechanisms are you debating? They're eliminations. What kind of eliminations? If I draw it the way I have it drawn right here, where I drew essentially the conjugate base of this,
That's E1C.
this is E1CB. Now, why might the E1CB mechanism make more sense?
Because OA H2. Wait.
Why might making this intermediate make sense?
Oh, because alcohol isn't the best leaving group.
Alcohol's not a great leaving group, but even better. Former, what is it? It's aromatic. You made again. It's an aromatic intermediate. Why not just stop? Or if we're gonna stop in the middle of the road, take a view at the top of the hill somewhere. Hey, at least we'll be aromatic, right? Little pit stop. It's pretty up here, right? We're back down looking down at aromatic product, right? You could do an E2 at this point, but I think E1CB maybe makes more sense just because this is an aromatic intermediate. All right, okay, the electrons come down. We kick out the OH. Now we got to our first, I believe, intermediate.
So you do not regenerate?
Well, so what do we just make?
Ethanol.
We made ethanol and OH minus, which will essentially serve just the same way ethanol did. The ethoxide did, right? We had to balance our charge, right?
Okay.
Got to balance our charge. Make sure if you haven't balanced your charge, you're not done yet. Number our carbons: 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. Now, we got this guy. And now it's going to react with what? It's going to react with phenyl-Grignard. Right? That's the first step. Where do you think this is electrophilic at? Which carbon? 7. Why? Because then who's going to get electrons? Carbon 1 will get electrons, and what kind of product is that going to make? You're making an aromatic intermediate again. It's either enolates or aromaticity. All right, so then let's just draw that out quick. There's your phenyl, negative charge, pi bond, number of carbons, 8, 7, 6, 1, 2, 3, 4, 5. All right, so we have an aromatic product. Whoop-de-doo. How are we going to go from here? The negative charge is going to move around because right, if you look back at our, right, if we go back to this, right, let's go back to what the heck are we going to again? Right, we're trying to make these guys, right? So if I number the carbons on these guys, 8, 7, 6, 1, 2, 3, 5, 1, 2, 3, 4, 5. We want the pi bonds between either 1 and 5 and 2 and 3, right, for one of them. So let's back that off again. Maybe we can see it now if I still have it shrunk down. All right. So I need to get a pi bond between, let's do the first one, 1 and 5. So to move electrons, all right, I'm going to move electrons this direction then, right? Yes? So that means during the workup, when I add in H+, right, that's second step, right, where you're adding in H+, that means this pi bond is going to go grab that H, right? And that means carbon 4, as it is here, is going to have that new CH bond. So that would get us to the first product. If I label this first product A, and this one B. This right here would get us to A. How do we get to B? We would just go the other direction. I'd have to redraw this, so I'm just going to... Oh, let's move the A and B together. Oh well. Fine. I'm going to redraw that intermediate. Never underestimate the power of just redrawing the same thing twice. As in, do it. Trying to do 4 things off the same intermediate tends to get yourself and your professor that's trying to grade it confused. All right. So let's redraw this. The negative charge is back on 1. But now we're going to move these electrons this direction because we want the pi bond between 1 and 2 and 3 and 4. So move that, and we're going to move there. Our H plus is floating around. And this final one, so now the new CH bond is going to be on carbon 5, which got the new CH bond there. So same intermediate getting us to A and B, 2 different products. The same intermediate can get us to 2 different products, right? Just based on resonance structures, right? Doing some resonance structures. Yeah.
Okay, 2 questions. One, why don't you make all 3 products?
You probably could.
Okay.
Absolutely. You probably would make, yeah, right? You'd probably make where this protonates, for sure. I just didn't.
Okay.
I was messing with you. Mostly.
Okay. And then the second one, this is just technical, but is the Grignard not ionically bonded?
It is ionically bonded, right? So I need to put a plus charge. I should put a plus charge here on that.
Okay. So it
Right.
doesn't matter if you show the bond or not?
Usually you don't. You can, but you don't. I mean, you can, but then you need to show those two. Those are the two electrons that really attack.
Exactly, okay.
Yep, exactly. Good.